Hello everyone. Let's now take a step ahead and look into the CMOS voltage transfer characteristics. So when we the name voltage transfer characteristics will be quite obvious as we go along. I'll come to the definition of voltage transfer characteristics in some videos from now. But for understanding the CMOS voltage characteristics, it becomes important to look into the MOSFET device characteristics in a different point of view. Okay, so we have been looking into the MOS device characteristics, the gate to source voltage, the threshold voltage, and so on, from a device point of view, from a device physics point of view. But now let's try to look into the device properties from a switch point of view. I'll introduce the term switch, what it exactly means from a MOSFET viewpoint. But let's try to look into let's try to bring up some terms over here. So okay, so we will have this MOSFET. It has source gate, and drain, as usual. We know. So we had been deriving few things. So I'm not specifying over here whether it's an NMOS or an PMOS. We are telling that it's just a MOSFET. It's just an MOS transistor, and this transistor works whenever your VGS, your gate to source voltage, is greater than VT. Okay, if this is your gate to source voltage, and why have I put a mod over here, and the reason is it could be an NMOS or an PMOS. In case of an NMOS, it's a positive VGS. Okay, in case of a PMOS, it's a negative VGS. So I've just specified a mod over here, and I've not biased this transistor to be an NMOS or a PMOS. I've just said it's an MOS transistor with a gate to source voltage as a mod of VGS. Okay, so whenever this mod of VGS exceeds greater than threshold voltage, this device turns on, and that's what we have been learning till now. We have been learning the device characteristics, and we have sufficient images to prove that the gate to source voltage, whenever this gate to source voltage goes greater than VT, your device turns on. Okay, so let's try to build some diagrams around it. So this is what we meant. You have your source to drain, and this is the controlling gate, the gate switch that we have over here, and it says that whenever your gate to source voltage or your mod of gate to source voltage is greater than mod of VT, your device turns on. So this diagram is very much self-explanatory. It says that the switch will get closed whenever your VGS is greater than equal to VT. Okay, and it says a mod of it. So in case of a PMOS, it could be a negative VGS, which should be greater than negative of VT. So the mod of it is basically explains everything. Okay, so that's the scene. That this diagram pretty much covers the characteristics of MOS. Let's try to just summarize what we talked just now. So the transistor will act as a switch whenever you're with an infinite off resistance, whenever your VGS is less than VT. So if your VGS is less than VT, the opposite case, the device is just switched off. And when I say switched off, this is an open circuit over here, so there is no current flow from source to drain. Okay, and whenever your VGS is greater than VT, which is the scenario which is mentioned over here, or which is the scenario which we have been talking for some time, whenever your VGS is greater than VT, this switch just closes, and you see a finite resistance from source to drain. Okay, usually it should be in an ideal case it should be a straight line, but in a real way you have some finite resistances which is playing a role over here, and this is a very important resistance which is basically a nonlinear characteristics of your current. So we'll come to the resistance part in a bit from now. Let's try to cover the MOSFET device characteristics first. Okay, so this particular diagram and this justification pretty much explains how does a MOSFET or a transistor behaves as a switch. Okay, so moving on, let's try to bias them. Basically, by biasing I mean we'll prepare an NMOS and we'll make an PMOS, and we'll try to connect them and obtain a CMOS out of it. Something like this. You have a PMOS, you have NMOS, and you have all these connections to behave so that this particular device behaves as a CMOS. Okay, so CMOS is complementary MOSFET. The name complementary comes because of the fact that that these are both complementary logic. So whenever one is off, the other one is on, and vice versa. That's why the name complementary MOS transistors. Okay, so we have this PMOS at the top, you have NMOS at the bottom. The source of NMOS is connected to the ground. The source of PMOS is connected to VDD, because that's how it will actually behave. your gate is connected to Vin, but both the gate are tied together and they're connected to the input potential. Both the drains of your PMOS and your NMOS are tied together to get the output potential. And we have a load. So load could be anything. The CL, capacitance load, it could be the loading of the next input transistor. It could be wire. It is basically summation of all whatever it sees at this point. Okay, so this point will be either connected to a long wire, or it will be connected with a short wire but with the MOSFET over here, with another CMOS inverter over here. So this CL represents all of them, and I'll talk about CL in a bit sometime from now, because that's again an important concept. We should be knowing what all capacitances exist and which dominates at what potential. Okay, so about the resistance of this particular PMOS and NMOS and about the capacitances will come in some time from now. We'll come to that point in some time from now. Okay, so this is how this is the way the reason I'm stressing on this potentials or on this particular diagram is that there are some very important conclusions that will be taking out of this one. For example, let me take one example. In this case, the calculation of VGS will differ by the value of potentials that you apply. In case of this particular NMOS, your gate to source voltage is this point minus this point. So for example, it's V in minus VSS. Okay, so if V in was 0, VSS was VSS is ground, which is already 0, your this potential becomes 0 volts. And as a result of that, since it's 0 volts, your MOSFET, your NMOS is off. Okay, for let's take another example. Let's say this is V, this is the gate, this is the source. So the VGS of your PMOS will be this point minus this point. Basically, whatever potential you see over here minus whatever potential you see over here. So when your input voltage is at 0 volts, this is at VDD volts, so your VGS is actually negative VDD volts, which is the full scale voltage, and as a result of that, your PMOS will get turned on because the VGS is greater than VT. Okay, so that's the importance of this connections or these node voltages, and we'll try to get this node voltages written down over here. Okay, so let's do that. So the first thing, when your input voltage is high, when your Vin is high and it is equal to VDD, so we are saying that this potential is equal to this potential. At that time, what happens? Okay, so when your Vin is VDD, your VGS, basically this point minus this point for NMOS, becomes VDD. So for example, if VDD was 5 volts, your VGS for your NMOS, which is this point minus this point, becomes 5 volts. Okay, so your VGS of NMOS is greater than VT and your NMOS turns on. Okay, on the other hand, your Vin, which is VDD, which is 5 volts, and this is again your VDD, which is 5 volts, and your VGS for your PMOS is 0 because it's VG minus VS, which is 5 volts minus 5 volts, it's 0, and as a result of that, your PMOS will get turned off because the voltage is less than VT. Okay, so your PMOS will get turned off for the reasons just explained, because your gate voltage VGS of PMOS is basically less than VT and it get turns off. In case, so this is how to represent it. Your PMOS is off, and if this is off, you can just open the PMOS. You can just represent the PMOS by an open switch. Okay, when your NMOS is on, let me come to NMOS now. So when your NMOS turns on, for the reasons that I just explained, when your gate voltage or VGS is greater than VT, your NMOS turns on, and the NMOS can now be represented by a resistor. Okay, and then we had the output load as well. So this is this situation when you see when your Vin is equal to VDD. Okay, this is just one scenario where we explain that what happens to the gate, how the gate to source voltage varies between PMOS and NMOS. Okay, and as a result of that, you see this is a scenario when your input voltage is VDD. So what we'll do, we'll stop at this point, as in the next video we'll try to do a reverse way where we put a Vin equal to VSS or Vin equal to 0 volts and try to derive similar kind of equation or similar kind of graph or similar kind of circuit diagram for that scenario as well. Okay, and as a result, and after that, we'll try to mix or merge these two scenarios and obtain the CMOS voltage transfer characteristics. So let's try to do all this in the next video. Thank you.